Why humans will never reach another star system. The real reason. Look up at the night sky and those stars feel close enough to touch. Ancient astronomers thought the same thing, measuring what they believed were modest distances to a celestial sphere just beyond where the air grows thin. We've built rockets that reach the moon, sent probes past Pluto, and convinced ourselves that reaching the stars is simply a matter of time and better technology. But the universe has embedded a permanent barrier into the fabric of reality itself, one that no amount of human ingenuity, determination, or future advancement can ever overcome. The real reason we'll never reach another star system isn't what you think, and understanding it changes everything about our place in the cosmos. Night dreams. On a clear evening, far from city lights, the stars appear close enough to touch. Ancient Mesopotamian astronomers tracked their movements across the dome of night, believing them fixed to a celestial sphere that rotated around Earth. The Greeks measured what they thought were modest distances, imagining the cosmos as a series of nested spheres, each carrying its celestial bodies in perfect circular motion. Chinese stargazers mapped constellations that told stories of emperors and dragons, while Polynesian navigators used stellar patterns to cross thousands of miles of open ocean, reading the sky as intimately as we might read a map. Every culture that looked upward shared the same instinctive reaction. These points of light felt reachable, like distant campfires on a dark plain. The human brain, evolved to judge distances across savannas and through forests, treated the night sky as simply another landscape to traverse. Aboriginal Australians spoke of ancestors climbing into the heavens. Norse mythology described a rainbow bridge connecting Earth to divine realms, and Hindu texts imagined gods travelling between celestial kingdoms. This wasn't mere poetry or primitive thinking. Our visual system processes nearby objects with remarkable precision, allowing us to catch a ball or navigate through a crowded market with ease. But this same system, when confronted with objects beyond our atmosphere, fails completely. The stars provided no context for distance, no trees shrinking into the background, no mountains revealing their remoteness through haze, no familiar objects for scale. They appeared as pinpoints, and pinpoints could be anything. A firefly across a garden or a lantern on a distant hill creates the same visual impression. Medieval scholars debated whether stars might be holes poked in a dark celestial curtain, allowing divine light to shine through. The distances they proposed would make modern astronomers laugh. Some suggested the firmament lay just beyond where the air grew too thin to breathe. When Galileo turned his telescope skyward in 1609, he revealed mountains on the moon, spots on the sun, and moons orbiting Jupiter. But these discoveries actually reinforced the illusion of cosmic accessibility. If a simple tube with glass lenses could reveal such detail, how far could these objects truly be? The dream of reaching the stars felt less like fantasy and more like destiny awaiting better technology. This deeply human longing drove every space-age vision that followed. Science fiction authors imagined sleek ships gliding between star systems, as casually as ocean liners crossing the Atlantic. Engineers sketched rockets that would shrink cosmic distances through clever design. The same optimism that built cathedrals and crossed oceans suggested that reaching the stars simply required enough determination and ingenuity. After all, human history demonstrated a pattern of conquering impossible distances, from walking across continents to sailing around the globe to eventually standing on the moon. Each barrier fell before human persistence. The stars waited as the next frontier, the next distance to overcome, but this confidence rested on a foundation of profound misunderstanding. What our eyes showed us bore almost no relationship to reality. Those friendly points of light, seemingly just beyond reach, existed at distances that would shatter every human intuition about space, time, and possibility. Distance trick. The nearest visible star to Earth, aside from our Sun, hangs in the southern sky as part of the Alpha Centauri system. On a dark night it shines steadily, unremarkable among thousands of similar points scattered across the celestial sphere. To the unaided eye, it might appear slightly closer than Sirius or marginally farther than Vega, but these distinctions feel academic, like judging whether a distant mountain peak is 10 or 15 miles away. Our visual system simply cannot process the truth. Alpha Centauri lies approximately 25 trillion miles from Earth. Written in numbers, that's 25 followed by 12 zeros, a figure that triggers no emotional response because human brains didn't evolve to comprehend such scales. We might as well be reading random digits. To grasp this distance requires anchoring it to something familiar. If you could drive a car directly through space toward Alpha Centauri, maintaining a steady 60 miles per hour without stopping for fuel or rest. The journey would take roughly 47 million years. Modern humans, Homo sapiens, have existed for only 300,000 years. Your drive would span more than 150 times the entire history of our species. The fastest car ever built, the Thrust SSC, which broke the sound barrier in 1997, would still require over 39 million years. Even this feels abstract. Consider instead that light moving at 670 million miles per hour takes 4.3 years to cross this gap. Nothing in human experience moves at remotely comparable speeds. A bullet travels at roughly half a mile per second. Light covers 186,000 miles in that same second. Yet, even travelling at this incomprehensible velocity, it takes over 4 years to reach Alpha Centauri. The deception runs deeper than mere distance. Our eyes show us stars as dimensionless points, suggesting they're all roughly similar in size and brightness. This creates the impression of a vast but navigable cosmic neighbourhood, like a city viewed from a hilltop where every light represents a reachable destination. Reality tells a different story. Some of those pinpoints are relatively nearby stellar embers, barely larger than Jupiter. Others are supergiant stars millions of times more luminous than our Sun, visible across thousands of light years. Betelgeuse, the reddish star in Orion's shoulder, lies approximately 550 light-years distant. If it were placed where Alpha Centauri sits, it would shine brighter than the full moon. Meanwhile, Proxima Centauri, actually the closest individual star at just 4.2 light-years, remains completely invisible to the naked eye, despite its proximity. Our visual system interprets this jumble of vastly different objects at wildly varying distances as a simple scatter of similar lights at comparable removes. The illusion persists even when we learn the truth. Standing under a dark sky, knowing that Alpha Centauri lies 25 trillion miles away, it still looks close. The same neurological machinery that helps us navigate our immediate environment actively sabotages our ability to grasp cosmic scale. Light's journey. Light moves at exactly 299,792,458 meters per second through vacuum. This speed represents not just the fastest thing we've measured, but according to Einstein's special relativity, the absolute speed limit of the universe itself. Nothing with mass can reach it. Nothing without mass can travel slower. When we say Alpha Centauri sits 4.3 light-years away, we're describing how long light takes to traverse that distance, but what does this actually mean in terms that connect to human experience? A light-year equals roughly 5.9 trillion miles, or 9.5 trillion kilometers. Light could circle Earth's equator 7.5 times in a single second. In 1 year, travelling at this blistering pace without pause, it would cover a distance so vast that representing it in miles or kilometers becomes almost meaningless. The numbers grow too large for intuitive comprehension. Instead, consider what light has travelled past during its journey from Alpha Centauri to your eye. 4.3 years ago, that photon began its trip. If you're reading this in 2025, it departed in 2021, when the world was still grappling with pandemic lockdowns and the Mars Perseverance rover had just landed on the red planet. The light reaching us tonight from more distant stars carries news from deeper in the past. Photons from Sirius, 8.6 light-years away, left that star when smartphones were less sophisticated and different songs topped the charts. Light from Vega, 25 light-years distant, began its journey when the internet was just becoming a household utility. The deeper implication reshapes how we think about cosmic connection. When we observe a star 100 light-years away, we see it not as it exists now, but as it appeared a century ago. We view a stellar photograph from 1925, when Schrödinger was developing quantum mechanics and the first television transmission had just occurred. That star might have exploded decades ago, its death throes expanding outward as a supernova, but we won't receive that information for generations. The universe comes to us as history, never as the present moment. This temporal separation reveals why reaching another star presents challenges beyond mere distance. Even if we could send a message at light speed, the absolute fastest information can travel, we'd wait 4.3 years for our signal to reach Alpha Centauri, then another 4.3 years for any response. A simple conversation would take nearly a decade. For stars hundreds or thousands of light-years distant, communication becomes effectively impossible across human lifespans. But the real barrier emerges when we consider travel rather than communication. Our fastest spacecraft, Voyager 1, launched in 1977, currently travels at roughly 38,000 miles per hour relative to the Sunday. This represents humanity's most distant ambassador, carrying a golden record of Earth sounds and images into the cosmic dark. At this velocity, Voyager would require over 73,000 years to reach Alpha Centauri if it were pointed in that direction, which it isn't. The spacecraft will instead drift silently through interstellar space, crossing no particular destination, long after human civilization has either transformed beyond recognition or ceased entirely. Cosmic desert. Between our sun and the nearest neighbouring star stretches a void so empty, so utterly devoid of matter, that the word emptiness barely captures it. Interstellar space contains, on average, roughly 1 atom per cubic centimetre. To grasp this sparseness, imagine scaling down the solar system until the sun becomes the size of a grain of sand sitting in New York City. On this scale, Alpha Centauri would be another grain of sand in London. Everything between these 2 points, the entire Atlantic Ocean, the breadth of a continent, thousands of miles of Earth's surface, would be almost completely empty. You might find a few dozen atoms scattered randomly across this entire distance, but otherwise nothing. No air, no dust, no particles of any kind. Just mathematical points in pure vacuum separated by distances that dwarf anything in our immediate environment. The sparse atoms that do exist in interstellar space cluster in clouds of hydrogen and helium, remnants of the Big Bang mixed with heavier elements forged in stellar furnaces and scattered by ancient supernovae. These diffuse clouds might reach densities of hundreds or even thousands of atoms per cubic centimetre in their thickest regions, still far more tenuous than the best vacuum ever created in a laboratory on Earth. Between these clouds, the density drops even further, to perhaps 1 atom per 10 cubic centimetres. For comparison, the air you're breathing contains roughly 25 quintillion molecules per cubic centimetre. The ratio defies comprehension. This emptiness extends in all directions without variation or landmark. Earth orbits the Sun in what astronomers call the local bubble, a region about 300 light-years across where ancient supernova explosions cleared away much of the interstellar gas, leaving even sparser conditions than average. Within this bubble, we sit in a cavity within a cavity, isolated not just from other stars but from even the thin material that loosely connects them. No trail markers indicate direction, no gradual transitions signal progress. A spacecraft leaving our solar system would traverse this void with nothing to measure its advancement except the slowly shifting angles of stars, points of light that would remain essentially fixed in position across decades of travel. The temperature of this emptiness hovers near absolute zero, roughly negative 270 degrees Celsius, just 3 degrees above the coldest possible temperature. The cosmic microwave background radiation, the afterglow of the Big Bang itself, provides the only heat, a faint whisper of energy left over from the universe's formation 13.8 billion years ago. This cold isn't like Arctic wind that strips heat from exposed skin. It's the temperature of nothing, of space that lacks sufficient matter to conduct heat away or deliver it. An object drifting through interstellar space would slowly radiate away its warmth into the void, approaching equilibrium with this background temperature over time. The desert contains no oases, no rest stops, no sources of fuel or repair. Unlike Earth's oceans, which teems with life and nutrients even in their deepest trenches, interstellar space offers absolutely nothing to sustain a journey. A ship departing for Alpha Centauri would need to carry everything required for the entire voyage. Every atom of fuel, every molecule of water, every spare part, every calorie of food. Nothing waits along the route to resupply or assist. The journey would be irrevocable, a commitment made at departure with no possibility of support or rescue once the solar system recedes behind. Speed limits. The universe imposes a maximum velocity that nothing, no particle, no spacecraft, no information can exceed. This cosmic speed limit, approximately 299,792,458 meters per second, emerges not from engineering limitations, but from the fundamental structure of space-time itself. Albert Einstein discovered this barrier in 1905 while working as a patent clerk in Bern, Switzerland, developing his special theory of relativity by examining what happens when objects approach extreme velocities. His equations revealed something profoundly strange. As an object accelerates closer to light speed, its mass effectively increases, requiring ever more energy to push it faster. A spacecraft traveling at 90% of light speed would possess more than twice its rest mass. At 99%, this factor jumps to 7. At 99.9%, it reaches 22. The progression continues without mercy. Each increment closer to light speed demands exponentially more energy, approaching infinity as the object nears the barrier. This isn't a technical challenge awaiting better engines or cleverer fuel. The energy requirement literally becomes infinite at light speed for anything possessing mass. You could harness the entire output of every star in the galaxy, and it wouldn't suffice to accelerate a single grain of sand to precisely the speed of light. The universe simply forbids it through mathematical law as inviolable as any physical constraint. Einstein's equations also revealed that time itself behaves differently at high velocities. For an object moving at 99% of light speed, time passes roughly 7 times slower than for a stationary observer. This time dilation isn't perceptual or illusory, it's a genuine physical effect confirmed by countless experiments. Atomic clocks flown on airplanes run measurably slower than identical clocks on the ground, exactly as relativity predicts. Particles called muons, created when cosmic rays strike Earth's upper atmosphere, should decay within microseconds, yet they regularly reach the surface because their high velocities stretch their lifespans from our perspective. The effect scales dramatically near light speed. At 99.999%, 5 nines a year passes for the traveller, while a century ticks by for everyone else. This temporal distortion offers no escape from the interstellar distance problem. Even travelling at this ludicrous velocity, the journey to Alpha Centauri would require 4.3 years from Earth's perspective, and while the traveller might experience the trip as lasting just days or weeks due to time dilation, they'd still arrive 4.3 years after departure according to every clock back home. Perhaps more crucially, photons themselves, particles of light that define this universal speed limit, possess no mass, which is precisely why they can travel at this velocity. Everything else carries mass, from electrons to entire spacecraft, binding them permanently below the threshold. Some particles can approach remarkably close. The Large Hadron Collider accelerates protons to 99.99999, 1% of light speed, so near the limit that they circle the collider's 17-mile ring over 11,000 times per second. Yet even these particles, despite consuming enormous amounts of energy and weighing roughly 1.6 times 10 to the negative 27 kilograms, cannot quite reach the barrier. Scale this up to a spacecraft massing thousands of tons, and the energy requirements become cosmically absurd. The laws governing our universe permit no exceptions, no loopholes, no clever tricks to circumvent this limit. Proposals for faster-than-light travel inevitably require exotic matter with negative mass, or the manipulation of space-time itself through concentrations of energy that dwarf anything achievable, or violations of physical laws that appear fundamental. The Alcubierre drive, for instance, theoretically contracts space ahead of a ship while expanding it behind, but the mathematics demand impossible quantities of negative energy. Wormholes might connect distant points, but they'd require exotic matter to hold them open, and they'd likely collapse before anything could pass through. These remain mathematical curiosities rather than engineering blueprints. The speed limit stands absolute, embedded in the very fabric of reality, rendering the vast distances between stars even more insurmountable than simple measurements suggest. Rocket reality. The fastest human-made object ever launched, the Parker Solar Probe, reaches speeds of approximately 430,000 miles per hour during its closest approaches to the Sunday. NASA designed this spacecraft to study our star's corona by diving repeatedly through the Sun's outer atmosphere, using Venus's gravity in a series of flybys to progressively tighten its orbit and increase its velocity. On its closest pass, the probe experiences temperatures exceeding 2,500 degrees Fahrenheit, while travelling fast enough to cross the distance from London to Tokyo in under a minute. This represents the absolute pinnacle of current propulsion technology, and it moves at just 0.064% the speed of light. At this velocity, the Parker Solar Probe would require approximately 6,700 years to reach Alpha Centauri. When it launched in August 2018, the Roman Empire had fallen only 15 centuries earlier. 6,700 years ago, humans were still developing agriculture in Mesopotamia, inventing the wheel, creating the first cities. The entire span of recorded human history fits into this travel time with millennia to spare. The Voyager 1 spacecraft, launched in 1977, currently holds the record as humanity's most distant emissary, travelling at roughly 38,000 miles per hour after receiving gravitational assists from Jupiter and Saturn. It crossed into interstellar space in August 2012, becoming the first human object to leave the Sun's immediate influence yet at its current speed. Voyager would need over 73,000 years to cover the distance to Alpha Centauri. The spacecraft carries a golden record containing sounds and images from Earth, along with instructions for playing it and a map showing our location using pulsar positions. This record will remain playable for billions of years in the vacuum of space, but Voyager will drift through the cosmic void long after human civilization has transformed beyond recognition or ceased entirely, never approaching any particular star. These velocities represent what's actually possible with chemical rockets, and gravity assists the only propulsion methods we've successfully used for interstellar distance spacecraft. Chemical rockets work by rapidly expelling mass in one direction, pushing the spacecraft in the opposite direction, according to Newton's third law. The energy comes from breaking chemical bonds in the fuel, the same process that occurs in a car engine or a campfire, just happening very quickly. The space shuttle's main engines burned liquid hydrogen and liquid oxygen, achieving exhaust velocities of roughly 10,000 miles per hour. Even this impressive performance pales against cosmic requirements. The fundamental limitation comes from the rocket equation, first formulated by Russian scientist Konstantin Tsiolkovsky in 1897. This equation relates the final velocity of a rocket to the velocity of its exhaust, and the ratio of its initial mass to its final mass. The mathematics are merciless. Achieving higher speeds requires exponentially more fuel. To double your final velocity, you need vastly more than twice the fuel you need enough to accelerate not just the spacecraft but all the additional fuel itself. Engineers speak of the tyranny of the rocket equation because it imposes hard limits on what's achievable. For interstellar travel, these limits become catastrophic. Ion drives offer somewhat better performance by using electricity to accelerate ions to much higher exhaust velocities, up to 90,000 miles per hour. The Dawn spacecraft, which explored the asteroid Vesta and the dwarf planet Ceres, used ion propulsion to achieve velocities impossible with chemical rockets, while using only a fraction of the fuel. But even ion drives operate within the same physical constraints. They trade fuel efficiency for thrust, producing acceleration measured in millimeters per second, rather than the powerful pushes of chemical engines. Dawn's ion engine generated less thrust than the weight of a single sheet of paper on Earth. Building up to interstellar velocities with such gentle acceleration would require decades of continuous operation and massive amounts of electrical power. Time problem. 4.3 light-years translates to approximately 25 trillion miles, and covering this distance with any foreseeable technology requires timescales that exceed individual human lifespans by orders of magnitude. Using our fastest current spacecraft as a benchmark reveals the brutal arithmetic of interstellar travel. Even if we could build a ship matching the Parker Solar Probe's record-breaking velocity and sustain it indefinitely, neither of which we can actually do, the journey would span roughly 6,700 years. A traveller departing today wouldn't arrive until the year 8,725. When such a ship finally reached Alpha Centauri, more than 270 generations would have lived and died on Earth since its launch. The pyramids of Giza are only 4,500 years old. This journey would take half again as long as the time separating us from their construction. Proposals for more advanced propulsion systems don't substantially improve these timescales with realistic assumptions. Nuclear pulse propulsion, conceived in the 1950s through Project Orion, would work by detonating nuclear bombs behind a massive shock absorber, riding the explosions like a ship surfing successive waves. Physicist Freeman Dyson calculated that such a vessel might reach 3 to 5% of light speed, reducing the journey to Alpha Centauri to roughly 86 to 143 years. This represents a genuine improvement over chemical rockets, but it still exceeds a human lifetime, and the engineering challenges are staggering. The spacecraft would need to carry thousands of nuclear devices and survive repeated atomic detonations, all while protecting its human cargo from radiation. Nuclear fusion drives, if we ever develop them, might push speeds to 10% of light speed, cutting the journey to 43 years. This approaches the realm of barely feasible for a human crew. Someone departing at age 20 might arrive at age 63, having spent their entire adult life in transit. Yet fusion propulsion remains theoretical. We've achieved fusion reactions in laboratories and weapons, but sustaining controlled fusion that produces more energy than it consumes has eluded researchers for decades despite billions invested in facilities like ITER in France. A functioning fusion reactor would revolutionize Earth's energy supply. A fusion drive capable of accelerating a massive spacecraft to relativistic speeds remains vastly more difficult. The numbers assume perfect conditions that don't exist. A spacecraft can't simply accelerate to maximum velocity and coast. It must also carry enough fuel to decelerate upon arrival, roughly doubling the energy requirement. The fuel for acceleration must be accelerated along with the ship, compounding the mass. Every additional kilogram of cargo scientific instruments, living quarters, life support systems, food, water, spare parts requires more fuel, which requires more fuel in a vicious cycle. These calculations also ignore the time needed to accelerate and decelerate. A ship can't jump instantly to 10% of light speed. It must build up gradually at accelerations the human body can withstand. Sustained acceleration beyond a few gravities would kill the crew through crushing forces. At 1 gravity, the acceleration we experience standing on Earth reaching 10% of light speed would require approximately a year of continuous thrust. This year must be subtracted from the coasting phase and matched by an equal deceleration period at the destination, extending the total journey time. The generation ship concept attempts to sidestep individual lifespan limitations by creating a self-sustaining community aboard a massive vessel. The original crew would have children, who would have children, across multiple generations until distant descendants finally arrived. But this introduces profound new problems: maintaining genetic diversity with a limited population, preventing social collapse over centuries, preserving knowledge and purpose across generations who know only the ship, ensuring critical systems remain functional for longer than any human institution has ever existed. Fuel impossibility. The mass of fuel required to reach even modest interstellar velocities defies not only engineering capability, but the fundamental physics of how rockets work. Consider the rocket equation's implications for a journey to Alpha Centauri. To achieve just 10% of light speed using conventional propulsion, a spacecraft would need a mass ratio, the ratio of initial mass including fuel to final mass without fuel that approaches absurdity. Chemical rockets, burning hydrogen and oxygen, achieve exhaust velocities of roughly 10,000 miles per hour. Light speed equals 670 million miles per hour, 67,000 times faster. The mathematics become brutal. For every kilogram of payload you want to deliver to 10% of light speed, you'd need exponentially more fuel. The specific calculation depends on the exhaust velocity, but with chemical rockets, the required mass ratio enters territory beyond astronomical. You'd need more fuel than exists in the entire solar system to accelerate a spacecraft massing just a few tons. Even switching to more efficient propulsion doesn't escape the fundamental problem. Ion drives achieve higher exhaust velocities, perhaps 90,000 miles per hour, but the mass ratio required for interstellar speed still climbs into impossible ranges. Nuclear pulse propulsion improves matters by effectively using nuclear explosions as exhaust, but each bomb adds mass that must itself be accelerated. Project Orion calculations suggested a minimum vessel mass of 4,000 tons for an interplanetary ship. An interstellar version would scale up proportionally. Launching 4,000 tons from Earth's surface requires overcoming our planet's gravity well, itself consuming enormous energy. The Saturn V rocket, the most powerful ever successfully flown, could lift 140 tons to low Earth orbit. Getting Project Orion's mass into space would require dozens of Saturn V equivalent launches, each costing billions in modern currency, just to assemble the ship before it even begins its journey. The fuel problem compounds when you account for deceleration. A ship accelerating to 10% of light speed must also slow down upon arrival, unless you're content with flashing past Alpha Centauri at 67 million miles per hour with no ability to stop or explore. This effectively doubles the fuel requirement you need, enough not just to reach cruising speed, but to carry the deceleration fuel along during acceleration. The mass ratio squares, pushing requirements from merely impossible to cosmically absurd. Antimatter represents the theoretically most efficient fuel possible. When matter and antimatter meet, they annihilate completely, converting 100% of their mass into energy according to Einstein's E equals mc squared. This perfect conversion offers energy density millions of times greater than chemical reactions or even nuclear fusion. Yet antimatter doesn't solve the problem, it merely shifts where the impossibility lies. Humanity has produced only infinitesimally small amounts of antimatter, measured in nanograms, at facilities like CERN. The energy required to create antimatter exceeds the energy released when it annihilates, making it an energy storage medium rather than an energy source. Creating the grams or kilograms needed for interstellar propulsion would require power generation beyond anything achievable. Storing antimatter presents equally insurmountable challenges, as it must never contact ordinary matter until you're ready for it to annihilate. Some proposals suggest harvesting fuel en route using magnetic scoops to collect sparse interstellar hydrogen, then fusing it for propulsion. The Bussard ramjet, proposed in 1960 by physicist Robert Bussard, would extend magnetic fields thousands of kilometers ahead of the ship, funneling hydrogen into fusion reactors. This elegant concept eliminates the need to carry all fuel from the start, but the engineering realities prove fatal. The magnetic fields would require enormous energy to generate and maintain. The drag from collecting interstellar medium would slow the ship, unless it achieved velocities where collection efficiency balanced thrust. The fusion reactors would need to operate continuously at efficiencies we've never achieved. Perhaps most problematically, interstellar space contains roughly 1 atom per cubic centimeter. The ramjet would need to process truly enormous volumes to collect usable fuel quantities. Human lifespan. A human body, evolved over millions of years to thrive on Earth's surface, begins deteriorating the moment it leaves our planet's protective embrace. The journey to Alpha Centauri, even at optimistic velocities like 10% of light speed, would span 4 decades. Enough time for a young adult to reach retirement age, while confined to a metal tube hurtling through the void. This assumes everything goes perfectly, that propulsion systems function flawlessly, that no critical failures occur during decades of continuous operation. Human bodies weren't designed for such durations in artificial environments. Our cardiovascular system, shaped by Earth's gravity, begins weakening almost immediately in weightlessness. Astronauts aboard the International Space Station lose roughly 1 to 2% of bone density per month in key areas like the hips and spine. A 4-decade journey would strip bones to dangerous fragility. 70-year-olds on Earth typically show 15 to 20% bone loss from peak density, but interstellar travelers would exceed this catastrophically. Their skeletons would become so brittle that the deceleration forces at journey's end might shatter them. Muscles atrophy similarly in microgravity. Without the constant work of supporting body weight against Earth's pull, muscle mass deteriorates at roughly 1% per week initially, slowing but never stopping. ISS astronauts exercise 2 hours daily on specialized equipment to counteract this loss, yet still return weaker than they departed. Maintaining muscle over 40 years would require similar dedication, assuming the equipment remained functional and motivation survived decades of identical routines. The human spine elongates in space as gravity no longer compresses vertebral discs, causing chronic back pain for many astronauts. This stretching, combined with muscle weakening, leads to problems that worsen over time rather than stabilizing. Cosmic radiation poses threats beyond simple exposure. Earth's magnetic field and atmosphere shield us from high-energy particles streaming from the Sun and from distant supernovae. A spacecraft traveling between stars would receive no such protection. Galactic cosmic rays, atomic nuclei accelerated to nearly light speed by violent cosmic events, would pass through hull and human tissue alike. These particles damage DNA directly, increasing cancer risk and causing cellular degradation. NASA estimates that a Mars mission, lasting 2 to 3 years, would expose astronauts to radiation equivalent to receiving a full-body CT scan every 5 to 6 days. An interstellar journey would multiply this exposure across decades. The cardiovascular system suffers under cosmic rays. Studies of astronauts who traveled beyond low Earth orbit during Apollo missions show elevated rates of cardiovascular disease years later, possibly linked to radiation damage. The brain itself may be vulnerable. Experiments with mice exposed to cosmic ray equivalents showed damage to neurons and behavioral changes persisting long after exposure. Human cognitive function might degrade gradually across decades of bombardment by particles our bodies never evolved to withstand. Vision deteriorates in space through a condition called spaceflight-associated neuroocular syndrome, where fluid shifts in the skull put pressure on the optic nerve. Some astronauts return from 6-month missions with permanent changes in eyesight. What happens after 40 years remains unknown, but the trend suggests progressive deterioration. Sleep disrupts in space. The 16 sunrises and sunsets visible daily from orbit confuse circadian rhythms. Interstellar travelers would lack even these cues, floating in unchanging darkness. Sleep deprivation compounds across years, affecting mental health, immune function, and cognitive performance. The psychological dimension grows severe at these timescales. The longest anyone has lived in space continuously is just under 15 months, achieved by Russian cosmonaut Valery Polyakov aboard Mir. He returned physically and mentally sound, but 15 months represents less than 4% of a 40-year journey. The isolation, confinement, and monotony of decades in a small spacecraft with the same handful of people would test sanity itself. Antarctic research stations, though on Earth with eventual escape possible, show elevated rates of depression and interpersonal conflict after just a few months of isolation. Marriage counselors note that even strong relationships struggle under constant proximity without escape. A crew trapped together for 40 years would face tensions without precedent. Every minor irritation would compound. Every personality quirk would become magnified. The immune system weakens in space. Astronauts show decreased immune response and reactivation of dormant viruses like chickenpox. On Earth, we constantly encounter microbes that keep our immune system active and primed. The sterile environment of a spacecraft, combined with stress and radiation, would leave crews vulnerable to any infection that did develop. With no hospitals or advanced medical care available. Food mathematics. The weight of food required to sustain a human crew across interstellar distances creates an insurmountable mass problem that multiplies every other engineering challenge. An adult human requires roughly 2,000 calories daily to maintain basic health, translating to approximately 1.5 kilograms of food. This seems manageable until multiplied across decades and crew members. A single person traveling for 40 years would need about 22,000 kilograms of food, roughly the mass of 4 adult elephants. A modest crew of 10 people requires 220,000 kilograms, approaching the mass of the space shuttle at launch. This assumes perfectly preserved food that never spoils, contains exactly the needed calories and nutrients, and requires no packaging. Water demands dwarf food requirements. Humans need roughly 2 liters daily for drinking, but this represents only part of total water use. Hygiene, medical needs, humidity control, and other systems consume additional amounts. Even with aggressive recycling recovering water from urine, sweat, and exhaled moisture, as the ISS does, some loss remains inevitable. The ISS recycles approximately 93% of water, an impressive achievement requiring complex filtration systems and constant maintenance. The remaining 7% must be resupplied regularly from Earth. An interstellar ship would lack any resupply option. Starting with generous reserves, that 7% loss compounds over decades into catastrophic totals. A 10-person crew using 50 litres of water daily would need about 730,000 litres across 40 years if recycling achieved ISS-level efficiency. Water masses 1 kilogram per litre. 730,000 kilograms of water equals the mass of more than 100 African elephants. Add the food mass, and we approach 1 million kilograms for consumables alone, before accounting for the spacecraft structure, propulsion systems, shielding, living quarters, or scientific equipment. The rocket equation returns to haunt this calculation. Every kilogram of food and water must be accelerated to interstellar velocity, requiring fuel. That fuel must itself be accelerated, requiring more fuel, in the vicious spiral that makes interstellar travel impossible. Chemical rockets can't achieve the needed mass ratios. Even exotic propulsion systems struggle. The consumables represent just one component of total ship mass, but their non-negotiable humans must eat and drink, or they die. Reducing food and water margins means accepting crew death as inevitable, which defeats the purpose of sending people rather than robots. Freeze-drying reduces food mass somewhat by removing water, but nutrients still require physical mass. A calorie of energy must come from actual molecules, carbohydrates, proteins, or fats, each with fixed mass. You can't compress nutrients beyond their molecular density. The most energy-dense foods, like pure fat, contain about 9 calories per gram. Even using optimally dense nutrition, 40 years of calories for one person requires about 9,000 kilograms of pure fat, and humans can't survive on fat alone. We need proteins, vitamins, minerals, fiber. Growing food aboard the ship seems like an elegant solution until you examine the requirements. Plants need light, water, nutrients, and atmosphere to photosynthesize. The energy for photosynthesis must come from somewhere on Earth. The sun provides this freely, but a spacecraft must generate electricity to power growth lights. Nuclear reactors or solar panels could theoretically supply this power, but both add enormous mass. The panels would need to face the sun, which grows dimmer as you travel outward, becoming useless beyond the outer solar system. Growing areas require volume and structural mass to hold soil or hydroponic systems. Wheat, rice, and potatoes contain mostly water. The edible portions represent small fractions of plant mass. You'd need vast farming areas to feed even a small crew, all requiring light, temperature control, pest management, and constant attention. Experiments aboard the ISS have successfully grown lettuce and small crops, but scaling this to feed 10 people for 40 years would require farming facilities massing many tons. The farming equipment, growth medium, seed stock, and maintenance systems add to the total ship mass, reducing the payload fraction available for actual propulsion fuel. Some proposals suggest bacterial or algal cultures as efficient food sources, growing faster than plants in smaller volumes. Spirulina, a blue-green algae, contains high protein and grows rapidly in controlled conditions. Yet even with algal cultures operating at maximum theoretical efficiency, the infrastructure required bioreactors, circulation systems, nutrient inputs, harvesting equipment adds significant mass. Humans can't survive on algae alone for decades. We need dietary variety to maintain physical and mental health. Radiation rain. Beyond Earth's protective magnetic cocoon, space fills with invisible particles moving at nearly the speed of light. Galactic cosmic rays originate from supernovae, exploded stars that scattered their atoms across the galaxy billions of years ago, accelerating some to incredible energies. These particles, mostly protons, but also heavier nuclei like carbon and iron, streak through the cosmos with such energy that nothing can stop them. A cosmic ray proton traveling at 99.9% of light speed carries kinetic energy comparable to a well-thrown baseball, but concentrated in a single subatomic particle. When this particle strikes matter, it doesn't bounce off, it plows straight through, ionizing atoms along its path and shattering atomic nuclei. Earth's magnetosphere deflects many of these particles, bending their trajectories away before they reach the surface. Our atmosphere absorbs the remainder through collisions with air molecules. By the time cosmic rays reach sea level, they've been converted into harmless secondary particles. Standing on Earth's surface, you receive negligible cosmic ray exposure. Step outside this protection, and the bombardment becomes relentless. Astronauts aboard the International Space Station orbit within Earth's magnetic field, still receiving some protection, yet their radiation exposure increases dramatically compared to surface dwellers. They accumulate roughly the equivalent of 8 chest X-rays per day. An interstellar spacecraft would travel beyond any magnetic shielding, through regions where cosmic ray intensity reaches its maximum. The particles arrive from all directions simultaneously. There's no shelter, no safe angle. They pass through spacecraft hulls as if the metal weren't there. Aluminum, the common spacecraft material, offers almost no protection against high-energy cosmic rays. Thicker shielding helps marginally, but cosmic rays are so energetic that practical thicknesses barely reduce their intensity. Some particles carry enough energy to trigger nuclear reactions when they strike atomic nuclei in the shielding material, creating secondary radiation that can be more dangerous than the original cosmic ray. Engineers call this effect secondary radiation generation, and it makes shielding counterproductive beyond certain thicknesses. Adding more mass creates more secondary radiation, providing little additional protection. Water and hydrogen-rich materials shield more effectively than metals because light nuclei absorb energy without producing as many dangerous secondaries. Proposals suggest surrounding crew quarters with water tanks, serving dual purposes as both radiation barrier and consumable storage. Yet the mass requirements return water sufficient to reduce radiation exposure to survivable levels would mass many tons, exacerbating the propulsion challenge. Calculations suggest that even with optimal shielding, cosmic ray exposure during a 40-year journey would dramatically increase cancer risk. The cells most vulnerable to radiation-damaged bone marrow, intestinal lining, eyes, reproductive organs would accumulate damage steadily across decades. Unlike acute radiation poisoning from nuclear accidents, which kills through massive cellular destruction within days, cosmic ray exposure causes gradual deterioration. DNA breaks accumulate, repair mechanisms become overwhelmed, and mutations propagate through cell lineages. The cardiovascular system shows particular sensitivity to cosmic ray damage. Studies of Hiroshima survivors revealed elevated heart disease rates decades after exposure to bomb radiation. Apollo astronauts who traveled beyond Earth's protective field show higher cardiovascular disease rates than astronauts who remained in low Earth orbit. The mechanism remains unclear, perhaps radiation damages blood vessel linings, or affects cellular structures in heart muscle, but the correlation persists across multiple studies. Solar radiation adds another dimension to the threat. The sun releases charged particles continuously through the solar wind, and occasionally erupts with massive bursts called coronal mass ejections. These events hurl billions of tons of plasma into space at millions of miles per hour. When directed at Earth, our magnetic field channels them toward the poles, creating auroras. A spacecraft beyond Earth's field would receive the full force. During major solar events, radiation levels spike to lethal intensities within hours. Astronauts on the Moon during the Apollo program lucked out. No major solar event occurred during their brief surface stays. An interstellar crew would face these events repeatedly across decades. The ship would need a heavily shielded refuge where crew could shelter during solar storms, adding more mass. No stops. The void between stars contains nothing that could assist a damaged spacecraft or replenish depleted supplies. Unlike ocean voyages, where ships can anchor at islands for repairs or resupply, or terrestrial expeditions that can hunt game and gather water, interstellar space offers absolute emptiness. The nearest star to our Sun lies 4.3 light-years distant. No intermediate waypoints exist, no cosmic rest areas, no emergency refuges. A ship departing for Alpha Centauri commits to a journey where any critical failure means certain death for the crew, with no possibility of rescue or external assistance. This changes every engineering calculation because reliability must approach perfection across timescales far exceeding anything humans have achieved. The International Space Station requires regular maintenance and replacement parts delivered from Earth. Components fail constantly. Pumps break down, electronics malfunction, seals deteriorate. Ground teams troubleshoot problems, and resupply missions arrive every few months carrying spare parts. The station has operated continuously for over 2 decades only through this constant care and replenishment. An interstellar spacecraft must function flawlessly for 40 years or longer with only the spare parts carried at launch. Every system needs redundancy, every critical component needs backups, but each backup adds mass that requires more fuel to accelerate. Engineers face impossible choices: carry more spares and reduce fuel margins, or carry more fuel and accept higher risk of irreparable failure. The harsh environment of space degrades materials over time. Seals become brittle, lubricants evaporate in vacuum, radiation damages electronics. Components that might last decades on Earth fail faster in space. The longer the mission duration, the more catastrophic these failure modes become. A seal that degrades after 15 years poses manageable risk for a Mars mission, but catastrophic danger for an interstellar voyage. Testing components for 40-year lifetimes in space conditions would require 40 years of testing, an impossible temporal paradox for mission planning. Computer systems must remain operational across decades, running software that can't be updated by ground control due to communication delays. Modern spacecraft receive software patches from Earth when problems arise, but an interstellar ship travels so far that radio signals take years to reach it. When Voyager spacecraft encounter problems, Engineers on Earth diagnose issues and upload solutions, but even Voyager, at the edge of our solar system, receives commands only about 20 hours after they're sent. A ship halfway to Alpha Centauri would wait over 2 years for any communication with Earth. By the time a problem was reported and a solution returned, the crew would be long dead if the issue was critical. This isolation demands autonomous problem-solving capability beyond anything we've programmed. The crew must diagnose and repair any failure using only resources aboard the ship. Medical emergencies illustrate the stakes brutally. On Earth, serious illness or injury leads to hospitalization with specialized equipment and expert care. On the ISS, medical emergencies can trigger early return to Earth within hours. An interstellar crew member who develops appendicitis, suffers a broken bone, or experiences cardiac arrest must be treated with whatever medical supplies and expertise exist aboard the ship. Surgical complications could prove fatal without intensive care capabilities. Dental problems, typically minor on Earth, become serious when there's no dentist. A severe toothache or abscess could incapacitate a crew member for days or weeks. Psychological crises carry similar weight. A crew member who becomes severely depressed or psychotic can't be hospitalized or removed from the environment. The social dynamics of a small, isolated group create pressure with no release valve. Conflicts between crew members that might be resolved by separation on Earth must somehow be managed when the antagonists share a confined space with no escape. Mutiny, while seeming like science fiction drama, becomes a realistic concern during decades of isolation. Historical accounts of long-sea voyages record numerous mutinies born from months of confinement, and those ships could at least see land eventually. The propulsion system must function without fail because there's no cosmic AAA service to provide a tow. If engines fail during acceleration, the ship might achieve insufficient velocity, extending the journey to centuries. If they fail during deceleration, the craft will shoot past the destination at relativistic speeds, continuing into deeper space forever. Money Mountain. Building a spacecraft capable of reaching another star would consume financial resources that dwarf the entire economic output of human civilization. The International Space Station, humanity's most expensive engineering project, cost roughly $150 billion across 3 decades of construction and operation, and it orbits just 250 miles above Earth's surface, close enough that supply missions arrive in hours. Scaling up to interstellar distances multiplies costs beyond any reasonable projection. The Apollo program, which landed 12 humans on the Moon during 6 missions, cost approximately $280 billion in today's currency. Those missions traveled to a destination 3 days away, stayed for at most 3 days, and returned within 2 weeks. The entire lunar surface lies closer than many communication satellites. An interstellar mission would require technology orders of magnitude more sophisticated, operating for decades rather than weeks, with no possibility of resupply or rescue. Simply keeping humans alive for 40 years in space demands life support systems that dwarf anything built for Apollo or the ISS. Every breath of air must be recycled, every drop of water purified and reused, every calorie carefully rationed. The ISS life support system cost billions to develop and requires constant maintenance by rotating crews who can return to Earth if problems arise. An interstellar version would need to function autonomously for decades without failure, and building such reliability into complex machinery demands extensive testing, multiple redundant systems, and exotic materials, each adding to costs. Propulsion represents the largest expense by far. Chemical rockets won't work, we've established, they lack the performance. Nuclear pulse propulsion, the most plausible near-term option, would require thousands of precisely engineered nuclear devices, each costing millions. The Treaty on the Peaceful Use of Outer Space, signed in 1967, forbids nuclear weapons in space, so international agreements would need renegotiation. The political costs alone would span decades of negotiation. Even if nations agreed, manufacturing thousands of nuclear charges to exact specifications, then somehow launching them into orbit without triggering global panic, presents challenges beyond purely technical. The spacecraft structure itself would mass thousands of tons, far too heavy for any single launch. Building it would require dozens or hundreds of heavy-lift rockets, each costing billions per launch with current technology. SpaceX has reduced launch costs dramatically, But even at optimistic projections of $1,000 per kilogram to orbit, launching 10,000 tons would cost $10 billion before the ship itself exists. That's just the cost of moving raw materials into space. Assembly in orbit would require space stations larger than the ISS, specialized robotic systems or space-suited workers operating for years, and logistics coordination exceeding anything attempted. The development costs precede all of this. Designing an interstellar spacecraft from scratch requires advancing multiple technologies simultaneously: better radiation shielding, more efficient propulsion, automated repair systems, advanced AI for navigation and problem-solving, closed-loop life support that operates for decades, and countless other systems. Each technology demands years of research and billions in funding. NASA's annual budget hovers around $25 billion. Developing interstellar technology would likely require several multiples of this, sustained across decades. Add the human cost: training crews for journeys they won't survive to complete requires recruiting people willing to die in space, far from Earth, never seeing home again. The psychological screening, training programs, and support systems for such crews would need developing from scratch. Their families would require compensation for losing parents, spouses, or children to an irrevocable journey. The global economy produces roughly $100 trillion in goods and services annually. A realistic interstellar mission might cost several $1 trillion, representing multiple % of global economic output sustained across the decades-long development and construction phase. This assumes no cost overruns, which have plagued every major space project in history. The James Webb Space Telescope, a single instrument, ballooned from $1 billion to $10 billion over its development. An interstellar spacecraft offers far more opportunities for unexpected complications and cost escalation. Even if humanity collectively decided to fund such a mission, an unprecedented level of global cooperation, the opportunity cost becomes staggering. Those same trillions could fund cancer research, climate change mitigation, poverty reduction, education, infrastructure. The political challenge of convincing Earth's nations to divert resources from immediate human needs to a mission whose participants won't return and whose scientific benefits won't materialize for generations approaches. Impossibility. Democracies struggle to fund projects extending beyond election cycles. Authoritarian regimes focus on maintaining power. No existing political system handles multi-generational commitments well, and an interstellar mission represents the ultimate long-term investment. Particle danger. At interstellar velocities, even dust becomes a weapon. The sparse atoms and molecules drifting through the space between stars, typically 1 per cubic centimetre, sometimes clustering in slightly denser clouds, pose negligible danger to objects moving at ordinary speeds. The Voyager spacecraft, travelling at 38,000 miles per hour, encounters these particles harmlessly. They might erode surfaces over millennia, but present no immediate threat. Increase velocity to 10% of light speed, 67 million miles per hour, and the physics transforms completely. A grain of sand, massing perhaps 1 milligram, carries negligible energy when stationary. Accelerate it to 10% of light speed, and it acquires kinetic energy equivalent to roughly 200 pounds of TNT. The collision releases this energy in a fraction of a second, creating temperatures exceeding those in stellar cores and pressure waves that vaporize metal. Even a single dust grain could puncture hull plating, destroy critical components, or kill crew members if it struck the inhabited sections. The spacecraft wouldn't just encounter one particle. Traveling through interstellar space at relativistic velocity means colliding with thousands or millions of atoms per second. Most are individual hydrogen or helium atoms, too small to cause catastrophic damage individually, but their cumulative effect resembles sandblasting. The leading edge of the ship would erode continuously, with surface atoms knocked free by the constant bombardment. Over years, this erosion could wear through shielding, exposing critical systems underneath. Engineers would need to design the ship with a sacrificial forward shield, accepting that this surface will gradually ablate away during the journey. The shield itself adds mass, perhaps many tons of material thick enough to survive decades of particle impacts, which must be accelerated along with everything else. Occasionally, the ship would encounter something larger than individual atoms. Interstellar space contains dust grains left over from stellar formation and planetary system evolution. These microscopic particles, typically measuring micrometers across, float through the void in unknown concentrations. Detecting them proves nearly impossible. They're too small to see with telescopes, too sparse to map in advance. A spacecraft might travel for months without striking anything significant, then suddenly encounter a dust grain the size of a period on a printed page. At 10% of light speed, such a grain would impact with the energy of several tons of TNT, creating a crater in any ordinary material. The explosion would send shock waves through the ship's structure, potentially causing cascading failures. Armor thick enough to withstand such impacts would mass enormous amounts, making the propulsion challenge even more impossible. The relative velocity determines collision energy through Einstein's equation relating energy to mass and velocity. At low speeds, kinetic energy increases, with the square of velocity doubling your speed quadruples the energy. Near light speed, relativistic effects amplify this further. A particle's effective mass increases as it approaches light speed from the ship's reference frame, multiplying the collision energy beyond classical predictions. This means that increasing ship velocity from 10% to 20% of light speed doesn't merely double the particle collision energy. It increases it by roughly 4 times, plus additional relativistic contributions. The faster you travel, the more dangerous every particle becomes. Some proposals suggest electromagnetic shields to deflect charged particles before they strike the hull. A powerful magnetic field, similar to Earth's magnetosphere but generated artificially, could in theory bend the trajectories of ionized atoms, causing them to curve around the ship. This sounds elegant until examining the requirements. The magnetic field would need to extend far ahead of the ship, many kilometers at least, to provide sufficient deflection distance. Generating such a field requires enormous electrical current flowing through superconducting coils, which need cooling to near absolute zero, which requires power, which requires massive generators or nuclear reactors. The infrastructure to create and maintain this magnetic shield would mass many tons and consume significant power continuously. Moreover, magnetic fields only affect charged particles. Neutral atoms and dust grains would pass through undeflected, requiring physical shielding regardless. Uncharged particles make up a substantial fraction of interstellar matter. The ship might carry lasers or particle beams to vaporize larger debris before collision, detecting incoming particles with radar or LiDAR and destroying them microseconds before impact. This demands incredibly fast reaction times. At 10% of light speed, the ship covers 20,000 miles per second, leaving almost no time to detect, target, and vaporize obstacles. The targeting system would need to operate autonomously at speeds beyond human reflexes, and the energy required to vaporize even small particles adds to the power budget. Communication gap. Radio signals travel at light speed, the fastest that information can move through the universe. But this velocity becomes cruelly inadequate across interstellar distances. A spacecraft traveling to Alpha Centauri would watch Earth recede until even instantaneous communication becomes a conversation spanning years. During the journey's first months, signals would take hours to reach home, then days, then weeks. Halfway to the destination, messages would require over 2 years to arrive at Earth, and another 2 years for any reply to return. A simple question: should we adjust course to investigate this anomaly? Wouldn't receive an answer for 4 years, by which time the anomaly would be billions of miles behind. This delay doesn't result from technical limitations or primitive equipment. It represents the fundamental speed limit of causality itself. No radio transmission, no laser beam, no quantum entanglement trick can carry information faster than light. Einstein's relativity establishes this as absolute law, backed by every experiment ever conducted. Fictional technologies like subspace radio or Ansible communicators violate physics as thoroughly as perpetual motion machines. The universe permits no shortcuts for information transfer. The practical implications devastate any notion of Earth-based mission control guiding an interstellar journey. When Apollo astronauts orbited the Moon, ground controllers monitored every system, advised on problems, and guided decisions. The communication delay just over 1 second each way barely affected operations. Even Mars rovers, operating with delays of up to 22 minutes, received detailed instructions from Earth for each day's activities. An interstellar spacecraft must operate completely autonomously. The crew would make every decision alone, facing emergencies without expert consultation, troubleshooting problems without engineering support from home. If something breaks in a way they can't repair, No amount of expertise on Earth could help in time to matter. The isolation cuts both ways. Earth wouldn't learn of disasters until years after they occurred. A catastrophic failure explosion, collision, life support breakdown might kill the crew instantly, but Earth would continue broadcasting messages and receiving silence for years before accepting what happened. The families of crew members would wait through this awful uncertainty, hoping for responses that would never arrive. Eventually, someone would calculate that sufficient time had passed for a reply to any conceivable message, and the mission would be declared lost. As the ship accelerates away from Earth, the Doppler effect compounds communication difficulties. The same phenomenon that makes a siren's pitch drop as an ambulance speeds away affects radio signals. Transmissions from the receding spacecraft would shift to lower frequencies, stretched by the relative velocity. At 10% of light speed, this shift becomes substantial. Signals transmitted at one frequency would be received at Earth significantly lower. Both ship and ground stations would need to compensate continuously for this drift, adjusting transmitters and receivers as the relative velocity changed during acceleration and deceleration phases. The inverse square law means that signal strength decreases with the square of distance. Doubling the distance quarters the signal power received. At interstellar distances, even powerful transmitters become whispers. The spacecraft would need massive antenna arrays and high-power transmitters to send detectable signals across light years. Earth would require equally sensitive receivers, massive radio telescopes dedicated to listening for the faint carrier wave from a ship that might take decades to reach its destination. The power requirements for interstellar communication add to the ship's already impossible energy budget. Transmitting enough signal to be heard across 4 light years might require kilowatts or megawatts of power sustained continuously, draining batteries or nuclear reactors that could otherwise support life support or propulsion. Yet maintaining contact with Earth might be psychologically essential for the crew, a tenuous thread connecting them to humanity even as they voyage beyond anyone's ability to help. The bandwidth available for interstellar communication would be minuscule compared to what we consider normal. Sending high-resolution images or video would consume hours or days of transmission time. Most communication would reduce to text messages, carefully compressed to minimize transmission duration. Each message timed carefully around the power budget and receiver availability. Gravity's grip. Escaping Earth's gravitational well requires approximately 11 kilometers per second, 25,000 miles per hour just to reach orbit, and this represents merely the first step. The Sun's gravity dominates our solar system out to distances exceeding those of Pluto, holding planets, asteroids, and comets in their orbits through the same invisible force that keeps us pressed against Earth's surface. A spacecraft attempting to leave the solar system entirely must overcome not just Earth's gravity but the Sun's far stronger pull, reaching what astronomers call escape velocity relative to the solar system itself. From Earth's orbital position, this velocity measures roughly 42 kilometers per second, nearly 94,000 miles per hour. Achieving this speed demands enormous energy, and this represents only enough to drift away slowly, not to reach another star system in reasonable timeframes. The fastest spacecraft ever launched, Parker Solar Probe and the earlier New Horizons mission to Pluto, used gravitational assists from other planets to boost their velocities beyond what their rockets alone could provide. New Horizons flew past Jupiter, using that giant planet's gravity to slingshot outward at nearly 58,000 kilometers per hour relative to the Sun, fast enough to escape the solar system, though it will coast through interstellar space for millennia without approaching any particular star. This velocity came from a combination of the most powerful rocket available, launched at precisely the right time, and a fortuitous alignment allowing the Jupiter flyby. Such opportunities arrive rarely. The planets must be positioned correctly, which happens only during specific launch windows that might span weeks every few years. An interstellar mission couldn't simply wait for optimal planetary positions. The energy requirements dwarf what gravitational assists can provide. Reaching 10% of light speed requires 300 times more velocity than New Horizons achieved, and kinetic energy scales with the square of velocity. This means the energy needed grows by a factor of 90,000, not a mere increase but an utterly different category of challenge. If we imagine using chemical rockets to reach interstellar velocities, the mass ratio would be so extreme that the fuel required would exceed the mass of the observable universe. Nuclear pulse propulsion or fusion drives might theoretically provide sufficient energy, But even these exotic systems must first escape the solar system's gravity, well before beginning the long acceleration to relativistic speeds. Every kilogram of spacecraft must be lifted away from both Earth and Sun, fighting against gravity throughout the acceleration phase. Earth's surface sits roughly 150 million kilometers from the Sun, deep within the star's gravitational influence. Climbing out of this well resembles rolling a boulder up a hill. It requires continuous effort, and stopping means sliding back down. A spacecraft that runs out of fuel before reaching escape velocity will fall back toward the inner solar system, perhaps crashing into Earth or Venus, or settling into an elliptical orbit where it languishes uselessly. The gravitational potential energy that must be overcome can be calculated precisely using Newton's equations, later refined by Einstein's general relativity. The numbers reveal why interstellar travel remains impossible. The energy needed to lift even a small spacecraft away from the Sun and accelerate it to relativistic speeds exceeds the total energy output of our civilization across many years. We currently generate roughly 18 trillion watts globally, all power plants, all engines, all energy sources combined. Sustaining this for 1 year produces about 5.7 times 10 to the 20th joules of energy. Accelerating 1,000 tons to 10% of light speed requires roughly 4.5 times 10 to the 20th joules, nearly an entire year of global energy output devoted to moving a single spacecraft, and this assumes perfect conversion efficiency with zero losses. No engine achieves perfect efficiency. Chemical rockets convert maybe 60% of fuel energy into kinetic energy. Nuclear systems might do better, but still lose substantial energy to waste heat and radiation. Account for realistic efficiencies, and the energy requirement doubles or triples. Add the energy needed to first escape Earth's gravity, then the Sun's, and the total climbs higher still. The rocket must also carry fuel for deceleration, otherwise it will flash past the destination star at 67 million miles per hour, unable to stop. Carrying deceleration fuel means accelerating that fuel during the first half of the journey, which requires even more fuel, spiraling into the tyranny of the rocket equation. Some proposals suggest using the destination star's gravity to decelerate, swinging around it in a tight hyperbolic orbit that bleeds off velocity. This sounds elegant but fails under examination. Approaching close enough to a star to achieve significant deceleration would take the spacecraft through lethal radiation and heat, likely destroying it before the maneuver completed. Temperature extremes. Interstellar space exists at a temperature barely above absolute zero, hovering around negative 270 degrees Celsius, just 2.7 degrees warmer than the coldest temperature physically possible in our universe. This isn't cold in the way winter feels cold, where air molecules steal heat from exposed skin. The void between stars contains so few particles that temperature becomes almost meaningless. There's simply nothing there to be hot or cold. What exists instead is thermal radiation, the faint afterglow of the Big Bang itself, permeating all of space as the cosmic microwave background. An object drifting through this emptiness doesn't freeze in the way water freezes. It radiates away its own heat into the void, slowly approaching equilibrium with this background temperature over time. A spacecraft generates heat continuously through electronic systems, life support machinery, and human metabolism. The crew breathes, moves, operates computers, all processes that produce waste heat. On Earth, this heat dissipates into the atmosphere through convection and conduction. In space's vacuum, convection cannot occur because there's no air to carry heat away. Conduction fails, similarly heat cannot conduct through nothing. The only mechanism remaining is thermal radiation, where objects emit infrared light proportional to their temperature. This radiation carries energy away gradually, but not efficiently enough for the heat-generating systems aboard a spacecraft. Engineers must design active cooling systems using radiators, large panels that maximize surface area for radiating heat into space. The International Space Station employs massive radiator arrays, extending from its central truss, glowing dully in infrared as they shed the station's excess heat. An interstellar spacecraft would require similar radiators, but sized appropriately for decades of operation. These radiators add mass and complexity, and they must remain functional throughout the journey. If radiator panels become damaged by micrometeorite impacts or mechanical failures, the ship would slowly overheat despite the surrounding cold. Electronics fail at elevated temperatures, life support systems malfunction, and crew quarters become unbearably hot. The paradox of space is that overheating poses a greater immediate danger than freezing, yet freezing remains a threat under different circumstances. If power systems fail, nuclear reactors shut down, solar panels stop generating electricity, the ship would lose its ability to maintain habitable temperatures. The heat generated by humans and residual warmth in the structure would radiate away within hours or days, depending on insulation. Temperatures inside would plummet toward equilibrium with the cosmic background. Water in pipes would freeze and expand, rupturing the plumbing. Exposed surfaces would contract from the cold, potentially cracking structural components or breaking seals. Any crew members would need to huddle in insulated emergency shelters with chemical heating packs, buying time while attempting repairs, but repairs become nearly impossible when tools and materials become brittle with cold. Temperature regulation on smaller scales creates additional challenges. Humans maintain body temperature around 37 degrees Celsius through metabolism, but we depend on environmental conditions to stay within a narrow survivable range. Too hot, and hypothermia sets in, core temperature rises above 40 degrees, causing organ failure and death. Too cold, and hypothermia kills through the opposite mechanism. The spacecraft must maintain crew quarters within this narrow band continuously for decades. Life support systems that control temperature on Earth-based stations or short missions might suffice for months, but interstellar timescales demand reliability that exceeds anything built. Redundant heating and cooling systems add mass. Spare parts for repairing failed components add more. Each addition makes the propulsion problem worse. Thermal expansion and contraction stress materials throughout the ship. Components in direct sunlight when near our sun during departure might heat to hundreds of degrees, while shadowed sections remain frigidly cold. The temperature gradient between lit and dark sides causes metal to expand on one side and contract on the other, inducing mechanical stress. Over years, these cycles could fatigue materials, creating cracks that propagate until structural failures occur. Deep space missions beyond our solar system face the additional challenge that solar energy becomes unavailable for heating. The sun's light follows an inverse square law: twice the distance means 1/4 the light intensity. By the time a spacecraft crosses beyond Neptune's orbit, sunlight has dimmed to less than 1,000th of Earth's intensity. Relying on solar heating becomes impractical. The ship must generate its own warmth through nuclear reactors or radioisotope thermoelectric generators, which produce heat from radioactive decay. These systems require fuel that gradually depletes through decay. Plutonium-238, commonly used in such generators, has a half-life of 88 years. During a 40-year mission, roughly a third of its radioactive decay would occur, reducing heat output proportionally. Engineers must either carry excess fuel at launch or accept declining temperatures as the mission progresses. Mental challenge. The human mind, evolved for social interaction within communities, begins deteriorating under prolonged isolation in ways that no amount of training can fully prevent. Antarctic research stations provide the closest Earth-based analogue to interstellar confinement, small groups isolated for months in harsh environments with no escape possible. Studies of winter-over crews at places like Antarctica's McMurdo Station and Concordia Station reveal predictable psychological patterns. During the first weeks, novelty and purpose sustain morale. By 3 months, irritability increases as the same faces appear across the breakfast table every morning. 6 months in, depression rates climb, sleep patterns disrupt, and interpersonal conflicts escalate over trivial matters. Some crew members withdraw socially, seeking solitude even within cramped quarters. Others become hostile or paranoid. These effects emerge despite careful psychological screening, extensive training, and the knowledge that escape becomes possible in a few months when transport arrives or weather permits evacuation. Now extend this timeline from 6 months to 40 years, roughly 80 times longer. Every annoying habit of every crew member would become magnified beyond tolerance. The person who chews loudly, clears their throat constantly, or tells the same stories repeatedly would drive others to fury through sheer repetition across decades. There's no walking away, no separate apartments to retreat to, no changing social circles. The same 8 or 10 people would constitute your entire social universe from departure until death. Psychologists studying confined environments note that group dynamics often stabilize initially, as people establish roles and hierarchies, but the stability proves fragile. A conflict that might resolve through separation on Earth, two people simply avoiding each other, cannot resolve aboard a spacecraft where every shared meal, every work shift, every maintenance task requires interaction. Grudges compound, resentments fester. Small slights remembered years earlier become grievances that poison relationships. The third quarter phenomenon, documented in polar research and submarine operations, describes a psychological crisis occurring roughly 75% through missions. Morale collapses, conflicts peak, and crew effectiveness deteriorates. This happens predictably even on 3-month missions. What happens at the three-quarter point of a 40-year journey, 30 years in, with 10 years remaining when everyone knows that nobody will ever see Earth again? When the initial purpose and excitement have long since evaporated into grinding routine, the monotony itself inflicts damage. Human brains require novelty and stimulation to maintain healthy function. Sensory deprivation experiments demonstrate that even hours in unchanging environments cause hallucinations and cognitive impairment. Prisoners in solitary confinement develop serious mental illness within weeks or months. An interstellar crew would experience a different kind of deprivation, not total sensory isolation, but environmental monotony. The same corridors, the same consoles, the same recycled air bearing the same faint metallic tang. The view outside never changes, stars remain fixed in their positions across years, providing no sense of motion or progress. Earth would dwindle to a point of light, then become indistinguishable from other stars, erasing the visual connection to home. Without external reference points marking progress, time loses meaning in psychological terms. Days blur together into an undifferentiated stream of sameness. Astronauts on the ISS combat this through structured schedules, regular communication with family, and the knowledge of eventual return. None of these solutions apply to interstellar crews. No mission control can provide real-time guidance or support. No family video calls can maintain relationships when signals take years to traverse the distance. No return date exists to anticipate. Crew members would know intellectually that they're traveling toward a destination, but emotionally, the journey would feel static, trapped in place while time drains away. Studies of long-term isolation identify key protective factors: sense of purpose, social support, communication with outside world, and hope of eventual release. An interstellar mission eliminates most of these. Purpose might sustain some crew members, but it cannot protect everyone across decades. Social support exists only among the small crew who themselves struggle psychologically. Generation problem. Proposals for generation ships attempt to sidestep individual lifespan limitations by creating a closed society that perpetuates itself across multiple generations during the journey to another star. The original crew would bear children, who would grow up aboard the ship, eventually bearing their own children, continuing across perhaps 10 to 20 generations until distant descendants arrive at the destination. This sounds elegant until examining the biological, social, and ethical problems that render it impossible. Human genetic diversity requires a minimum population to avoid inbreeding depression, the accumulation of harmful recessive traits that occurs when closely related individuals reproduce. Population genetics calculations suggest that maintaining healthy genetic diversity across multiple generations requires several hundred individuals at minimum, with estimates ranging from 500 to several thousand depending on assumptions about genetic screening and medical intervention. Launching a crew of 500 multiplies. Every other challenge life support systems must sustain this population. Food and water requirements increase proportionally. Living space must expand dramatically. The spacecraft's mass would escalate beyond anything propulsion systems could handle. Attempting the journey with a smaller founding population invites genetic disaster within generations. Even with careful genetic screening and family planning to maximize diversity, a crew of 50 or 100 would face inevitable genetic bottlenecking. Harmful recessive alleles present but unexpressed in the founding population would become more common as the gene pool narrowed. Birth defects would increase. Genetic diseases would emerge, and fertility might decline as inbreeding effects accumulated. Within a few generations, the population could become non-viable. The social dynamics of a generation ship create pressures that no human society has successfully navigated. Children born aboard the ship would know nothing except the vessel's corridors, They would never experience rain, wind, sunlight on skin, the vastness of open landscapes. Their entire existence would unfold in recycled air, under artificial lights, within metal walls. Earth would exist only as abstract concept, a mythical place described by parents and grandparents but never experienced. Why should these children accept their role in a mission they didn't choose? The founding crew volunteered, understanding the sacrifice. Their children and grandchildren have no such choice. They're born into a purpose imposed by ancestors, compelled to maintain systems and continue the journey toward a destination they'll never see. History provides no precedent for sustaining multi-generational purpose without external reinforcement. Religious pilgrimages sustain themselves across generations through deep cultural belief, but even these eventually fragmented or lost their original purpose. Political movements rarely survive unchanged across more than 2 or 3 generations. The knowledge and skills required to operate and maintain an interstellar spacecraft would need perfect transmission across generations. Engineers born aboard the ship must achieve the same competence as the original crew, despite having no opportunity for formal education in universities, no access to outside expertise, no alternative career paths. Every critical role propulsion specialist, life support engineer, medical doctor, physicist must be filled continuously across decades. What happens when a generation produces insufficient children interested in or capable of maintaining nuclear reactors? Societies cannot command interest and aptitude to distribute according to need. Some generation would inevitably face shortages in critical skills, leading to system failures as equipment breaks down without qualified repairs. The ship's social structure would drift inevitably toward authoritarianism. Maintaining course toward a destination decades or centuries away requires suppressing dissent and enforcing compliance with mission parameters. Individual freedom must be subordinated to collective survival. Birth rates would need strict regulation to prevent overpopulation or underpopulation. Too many children strain resources. Too few threaten genetic viability and workforce replacement. Relationships, reproduction, career paths, resource allocation all would require central planning and enforcement. History suggests that authoritarian systems eventually collapse or transform, but a generation ship cannot tolerate political upheaval. Revolution or civil war aboard a spacecraft means mission, failure, and probable extinction for everyone. Physics wall. The laws governing our universe exist as mathematical certainties, not engineering challenges awaiting cleverer solutions. Einstein's equations describing space-time, the conservation of energy and momentum, the speed of light as an absolute limit, these aren't temporary obstacles that future technology might circumvent. They represent the fundamental architecture of reality itself, tested through countless experiments across a century of physics research and confirmed every single time. When we say nothing can exceed light speed, this isn't cautious pessimism or failure of imagination. It's recognition that accelerating mass to light speed requires infinite energy, a mathematical impossibility embedded in the structure of space-time. Special relativity, published by Einstein in 1905, emerged from examining how light behaves and asking what this implies about space and time. The equations revealed that mass and energy relate through his famous formula, energy equals mass times the speed of light squared. This relationship means that as objects approach light speed, their effective mass increases, requiring ever more energy to accelerate further. The curve approaches infinity asymptotically, meaning you could pour all the energy in the universe into accelerating a single atom and never quite reach that final threshold. Proposals for faster-than-light travel inevitably require exotic physics, negative mass. Wormholes stabilized by matter that violates every known law, or warping spacetime itself in ways that demand energy densities trillions of times beyond anything achievable. The Alcubierre drive, a theoretical concept from 1994, suggests contracting space ahead of a ship while expanding it behind, allowing the vessel to effectively move faster than light without locally exceeding that speed. The mathematics work on paper, but they require negative energy density, a property that no known form of matter possesses. Quantum field theory permits temporary negative energy fluctuations at microscopic scales through mechanisms like the Casimir effect, where two metal plates placed nanometers apart experience attractive force from quantum vacuum fluctuations. Yet scaling this to macroscopic dimensions, creating stable regions of negative energy large enough to envelop a spacecraft, violates energy conditions that appear fundamental to preventing causality violations. Faster-than-light travel creates temporal paradoxes. Objects moving faster than light could theoretically arrive before they departed from the reference frame of certain observers, enabling effects to precede causes. The universe seems to forbid this through the same laws that limit velocity. Wormholes, theoretical tunnels connecting distant points in space, suffer similar problems. Einstein's general relativity permits their existence mathematically, but maintaining an open wormhole requires threading it with exotic matter, possessing negative mass to prevent gravitational collapse. Even if such matter existed and could be manipulated, traversable wormholes would likely be microscopic and unstable, collapsing before anything could pass through. Proposals to hold them open long enough for human passage require energies comparable to stellar output sustained continuously. Quantum entanglement, often misunderstood in popular science, doesn't provide a communication loophole. When two particles become entangled, measuring one instantly affects the other regardless of distance, but this correlation cannot transmit information faster than light. The measurements yield random results until compared, and comparing them requires classical communication at light speed or slower. Every attempt to use entanglement for faster-than-light signaling has failed, not through experimental limitation, but because the quantum mechanical laws governing entanglement specifically prevent information transfer. The energy requirements for interstellar travel don't result from inefficient engines or poor design. They emerge directly from the kinetic energy formula. The energy needed to accelerate mass to a given velocity equals 1/2 the mass times velocity squared, with relativistic corrections at high speeds that make the situation worse. Accelerating 10,000 tons to 10% of light speed requires roughly 4.5 times 10 to the 20th joules. This energy must come from somewhere either carried as fuel, collected en route, or beamed from external sources, and every option crashes against physical limits. Carrying sufficient fuel violates the rocket equation. Collecting interstellar hydrogen faces the problem that space is effectively empty. Beaming energy across light years suffers from diffraction that spreads laser beams wider than planets at such distances, making targeting impossible. Some physicists speculate about new physics beyond our current understanding theories involving extra dimensions, modifications to general relativity, or as yet undiscovered particles with exotic properties. While new physics might emerge, nothing suggests it would enable faster-than-light travel or reduce energy requirements for interstellar journeys. The standard model of particle physics and general relativity together explain every phenomenon we've ever measured with extraordinary precision. New discoveries tend to operate at extreme scales, the first fractions of a second after the Big Bang, the event horizons of black holes, or the quantum realm of individual particles not in regimes relevant to spacecraft propulsion. The universe operates according to rules that permit stars, planets, life, and consciousness. But these same rules make interstellar travel effectively impossible for beings constructed of matter and constrained by thermodynamics. Beautiful acceptance. Understanding the true barriers to reaching other stars transforms how we see our place in the cosmos, revealing Earth not as a starting point for unlimited expansion but as a singular sanctuary in an ocean of inaccessible distance. The ancient human dream of spreading across the galaxy assumed that space represented merely a larger version of the terrestrial frontiers our ancestors crossed, more dangerous perhaps, requiring better ships, but fundamentally similar. We imagined the stars as islands in an archipelago, distant but reachable with sufficient determination. The physics tells a different story. The stars aren't islands in a traversable ocean. They're isolated kingdoms separated by gulfs so vast that the very laws of nature forbid crossing them with living passengers. This realization doesn't diminish the universe's wonder but deepens it. Those points of light scattered across the night sky each represent entire solar systems forever beyond our physical reach. Worlds we can study through telescopes and imagine through physics, but never walk upon or directly sample. Alpha Centauri, our nearest stellar neighbour, might host planets where alien sunsets paint unfamiliar skies, where chemistry produces compounds Earth has never seen, where evolution, if it occurred, took paths completely divergent from our own. We can deduce these possibilities, model these scenarios, but the 4.3 light-years separating us create an absolute barrier to direct exploration. Every star visible to the naked eye, every galaxy photographed by our telescopes, exists as an object of study rather than a destination. This permanence of isolation makes Earth precious in ways that unlimited expansion could never achieve. If humans could readily journey to other stars, Earth would become one planet among billions, its uniqueness diluted by infinite alternatives. But Earth isn't one option among many. It's the only place in the universe where beings like us can exist, the only world we'll ever directly experience, the only garden we'll ever tend. The fragility becomes apparent through this lens. We cannot escape to other worlds if we render this one uninhabitable. No backup planet awaits colonization. No frontier offers escape from ecological collapse or nuclear catastrophe. Everything humanity has created, all art, music, literature, science, all the accumulated knowledge and culture of our species, exists only here, on this small world orbiting an ordinary star. The distances that trap us here also protect us. If interstellar travel were possible, if some alien civilization possessed technology to cross the light years, Earth would be vulnerable to contact, colonization, or conquest. The universe's vastness provides isolation that works both ways. Whatever life might exist on planets circling distant stars remains there, developing according to its own trajectory, never crossing paths with us. Each world becomes an independent experiment in how chemistry can organize into biology, how evolution shapes complexity, how consciousness might emerge from matter. The diversity of life on Earth, millions of species, countless adaptations, the sheer inventiveness of evolution across 4 billion years represents just one outcome from one planetary environment. Thousands or millions of other worlds might host their own experiments, each producing different solutions to similar problems. Birds evolved flight through feathers and hollow bones. Alien life might achieve the same through entirely different structures. Brains process information through networks of neurons. Alien cognition might use completely different architectures. We can study these distant worlds through astronomy and physics, learning how planets form around different types of stars, which atmospheric chemistries might indicate biological activity, where conditions could permit liquid water or other solvents that enable complex chemistry. Each discovery adds to our understanding of how common or rare life might be, how varied its expressions could become. The search for extraterrestrial intelligence continues through radio telescopes listening for artificial signals, optical observatories watching for anomalous patterns, and instruments designed to detect atmospheric biosignatures in exoplanet spectra. These searches acknowledge the barrier we cannot visit, but perhaps we can communicate or simply detect evidence of life's presence. Even communication faces cruel limitations. The nearest potentially habitable exoplanets lie dozens of light years distant, meaning any radio conversation would require decades or centuries for exchanges. Yet this remains our only option for learning about life beyond Earth. New perspective. The impossibility of interstellar travel redirects humanity's cosmic ambitions from physical expansion toward deeper understanding of our local environment and the universe beyond our reach. Our solar system, once seeming insignificant compared to the galaxy's billions of stars, transforms into humanity's entire accessible domain, an intricate system of worlds, moons, asteroids, and space containing resources and environments sufficient for millennia of exploration. Mars beckons not as a waypoint to the stars, but as a destination in itself, a planet with valleys deeper than Earth's canyons, volcanoes dwarfing Everest, and polar ice caps that might preserve records of ancient climates. The journey requires only months rather than decades, distances measured in millions rather than trillions of miles. Establishing permanent settlements on Mars presents genuine challenges: radiation exposure, dust storms, toxic soil chemistry, isolation from Earth, but challenges that engineering can address without violating physics. The moons of Jupiter and Saturn offer equally compelling destinations. Europa's subsurface ocean, warmed by tidal flexing from Jupiter's gravity, might harbour life that evolved completely independently from Earth. Landing probes that drill through kilometres of ice, then deploy submarines to explore alien seas, represents one of humanity's most profound possible discoveries, finding life that originated separately from our own. Titan, Saturn's largest moon, possesses lakes and rivers of liquid methane beneath a thick nitrogen atmosphere. Its chemistry operates at temperatures where water freezes solid as rock, Yet organic compounds rain from the sky and accumulate in dunes of hydrocarbon sand. Understanding how chemistry behaves in such environments expands our conception of what planetary surfaces can be. The asteroid belt contains millions of bodies rich in metals and minerals, some potentially holding water ice. Rather than viewing asteroids as hazards to avoid, we might see them as resources enabling construction of habitats and infrastructure in space, without hauling everything from Earth's deep gravity well. Mining asteroids, refining materials in zero gravity, building structures that never need to withstand planetary gravity or atmosphere. These activities could support populations living and working in space without settling planets at all. Space-based civilizations, constructed from asteroidal materials and powered by solar energy, might eventually dwarf Earth's population while remaining within our solar system. Rotating habitats, providing artificial gravity through centrifugal force, agricultural facilities growing food in controlled environments, industrial facilities manufacturing goods in vacuum. None of this requires breaking physical laws or achieving impossible velocities. The same technologies developed for interstellar missions, closed-loop life support, radiation shielding, long-duration spaceflight find practical application within our solar system, enabling exploration and settlement across accessible distances. Our sun provides more than enough energy for civilization's needs. The total solar energy striking Earth every hour exceeds humanity's current annual energy consumption. Capturing even a tiny fraction through orbital solar arrays could power civilization for as long as the sun continues fusing hydrogen, another 5 billion years. Understanding the universe, even regions we cannot visit, continues advancing through astronomy and physics. Telescopes grow more sophisticated, detecting smaller and more distant planets, analyzing their atmospheric compositions, identifying which might host conditions suitable for life. The James Webb Space Telescope, launched in 2021, observes the universe in infrared wavelengths that penetrate cosmic dust, revealing stellar nurseries and the earliest galaxies formed after the Big Bang. Future observatories might detect biosignatures, oxygen and methane simultaneously in exoplanet atmospheres, suggesting biological activity, or even technosignatures indicating technological civilizations. Mathematics and physics allow us to model stellar evolution, simulate galaxy formation, understand black holes, and probe the nature of dark matter and dark energy. These investigations proceed through observation and theory rather than direct sampling, but the knowledge gained rivals or exceeds what physical exploration might provide. We comprehend the nuclear fusion occurring in stellar cores, the dynamics of accretion disks around black holes, the expansion of space-time itself, phenomena we'll never experience directly, but can model with equations that match observations precisely.